Hi, everyone. Thanks for joining. My name's Nathan. I'm one of the marketing managers at Data Science Dojo. I have Zia Hydari here with us today, and he's going to be presenting Miles to Go Before I Sleep, Health Wearables, Gamification, and Healthful Activity. If you have any questions during the presentation, you're welcome to ask them live. Go ahead and raise your hand, and we'll give you a live mic, and you can ask your question. The live stream is being recorded, so if you don't want your voice recorded, go ahead and send us the question in chat and we'll make sure it gets answered. All right, Zia, all yours.
Okay, thank you so much, Nathan, for that kind introduction. And as Nathan mentioned, my name is Zia Hydari, and I'm an assistant professor at University of Pittsburgh. And this is basically a piece of research we did using or a study that we conducted at University of Notre Dame. So I'm going to go over it with you. And let me just go on to the beginning slide. So before I go on, I have a little bit of understanding of what the bootcamp does, the Data Science Dojo bootcamp does. And my understanding is that most of you have interest in machine learning or data analysis, which is known as predictive analytics. And you've also been introduced to a randomized control trial. Just as a show of hand, if I may, dichotomy between predictive analysis and causal analysis. And I mean, I would really love if somebody could actually just come in and maybe verbalize what they think about the differences. Anyone? Okay, so let me just do it, and I would encourage all of you to sort of stop me and ask questions, make it as interactive as possible. And the reason being is my understanding is that most of you are, some of you are experts, most of you are familiar with what is predictive analytics, and for some of you, causal analysis might be something slightly different. So if you make it a conversation, I think everybody would enjoy the time more. So let me begin by describing what the difference is. So predictive analysis is, you learn about predicting an observable. So an example would be cancer by using sort of labeled radiological images. And the object of interest, which is cancer, is observed. So later on, the patient may actually exhibit cancer. So you're able to sort of get a lot of labeled data. Predictive analytics is a hard problem. You need a lot, at least for supervised learning, you need lots of correctly labeled data, right? Causal analysis is slightly different, so it is also a database technique. However, the goal is slightly different. The goal is learn, and as an example, you want to learn if things like smoking or asbestos or a new chemical agent, whether it causes cancer to an individual. The object of interest, which is basically the effect size, which is sort of an abstract object, is really not observed. Another example would be, which is sort of relevant in the current environment, is whether things, a drug such as hydroxychloroquine cures COVID-19. So as you can imagine, I mean, this is a much harder problem in general. The issue is that we often use similar statistical techniques. For example, regression is used in both types of analysis, whether it's predictive or causal analysis. But the difference is subtle and extremely important. A lot of times people are doing predictive analysis and trying to give it sort of a causal flavor, which actually is not correct. Okay. Any questions or comment on this point before I move on? Okay, so what is the fundamental problem of causal inference? This, is a well-known problem. The causal inference has a very long and storied history. A lot of philosophers have written about it. for example, John Stuart Mill and others, said it goes back hundred of years. Human beings have been trying to understand whether something causes another thing or not, and it is a very hard problem. But this is sort of a very succinct statement of the problem by the statistician called Paul Holland, which I sort of changed a little bit to create to remove sort of the abstract statement that he made and made it a little bit concrete with an example. So the fundamental problem is that it is impossible to observe. Let's say you're looking at a COVID-19 outcome, say lung damage or mortality because of COVID-19, with or without hydroxychloroquine used for the same individual. It is impossible to observe the same individual under both these conditions. So if there is an individual with sort of COVID-19 and you give them hydroxychloroquine, you can only observe their outcome under use condition. If you don't give them hydroxychloroquine, you can only observe the outcome under the condition that they did not use it. You cannot observe the same individual in the same time period in both these states. So because you cannot observe the effect of hydroxychloroquine on COVID-19 on an individual, this is kind of a fundamental problem. You cannot infer whether hydroxychloroquine on that particular individual, what is the effect, okay? So what do we do? How do we solve this issue? Or how do we do causal inference? I mean, one of the techniques that we widely use is randomized controlled trials, or RCTs, which I believe is part of the curriculum that is taught by Data Science Dojo, one of the modules. So if you have, in large samples, you can give a treatment or put a treatment to one group, such as a treatment like hydroxychloroquine, and then also you have another group to which you do not give the treatment. If you randomize the treatment, then what happens is that the group that receives the treatment and the group that does not receive the treatment, they will have roughly similar characteristics. And so we can estimate what is known as the average treatment effect, or average effect of whatever intervention you had. However, RCTs are many times not possible. They may be infeasible. For example, if I take let's take the example of electronic medical records or ERP systems or some kind of big IT system, and if you want to test whether this IT system has an impact on a firm, your manager is not, or CEO of the firm is not going to let you run an experiment, right? Or 100 firms are not going to let you run an experiment to see whether the whatever software you are using is beneficial or not. So hence, RCT would not be feasible in that situation. Another example would be an ethical concern, right? So if something is known or you suspect it's going to be harmful, like smoking, you cannot randomize individuals to something that might be harmful for them. Hence, sometimes you cannot do RCTs. So what is the solution then? The other thing you could do is what are known as observational studies, right? In this particular case, what you have is data that you may have observed, and you have data about both individuals who are sort of in the treated state, whatever the intervention may be, and the untreated state. And then you estimate or predict the counterfactual for the treated group from the data. So, you could imagine the case where you may have, and there is, by magic or for some reason, there is another exactly the same individual with which is every characteristic, every gene and DNA is similar, hypothetically. and you give the treatment to one individual and not to the other, who's an exact replica, then in that case, you would sort of observe the outcome in both the treated state and the untreated state. And then you can sort of find the difference and estimate the effect. Okay. So, this whole idea of causal inference is extremely important for firms. As managers or workers in a firm, what you really want to do is, if you take a decision, you want to know the effect of the decision on a particular outcome. So, if I do X, what would be the effect on my revenue? If I do Y, what would be the effect on profit? If I do Z, what would be the effect on the number of customers I have? Okay. So you are interested in finding the effect or the causal effect of various decisions you take in a firm. And that's what you're more, that's going to be a more weighty thing for you to know. Prediction, a lot of problems are prediction problems, and machine learning has, sort of helped with this, availability of large data sets, a lot of computing, these newer algorithms has solved a lot of problems. So one example, of course, is image and image recognition, or voice and voice recognition. These are applications that have been enabled by machine learning and by solving these prediction problems. However, many firm level decisions, or what people in firms want to solve, are essentially causal problems. You want to find the effect of a particular decision on an outcome. Hence, knowing about the subtle differences as well as how to do these studies is actually quite important. So let me take a pause before I kind of transition into the study, the actual study, and see if anybody has a question or comment about this preamble that I just described to you.
Zia, Raja here. When I look at both these bullets, right? So to me, they look the same, right? So in one case, I'm randomizing and I'm creating a randomized control trial. In the next one, observational studies, you're saying you're still picking up random individuals as treated and untreated. So to a layman, how would you differentiate between the two? To a layman, it might look like a play on words, right? So, yeah, I mean, in one case, you're randomizing. In another case, you're saying, okay, yeah, they are already, some ended up getting the treatment, others ended up not getting the treatment. And we randomly pick individuals. So it's almost like play on words. I mean, so can you just maybe elaborate a little bit on difference between observational study and RCT?
Yeah, absolutely. I think this is really a great question, and hits the crux of the problem. So, so in an observational study, basically individuals self-select into whatever the treatment may be. There is no randomization per se of the treatment. So in the first case, the randomized controlled trial, let's say, for example, if you take the example of a firm that is doing some change on they have a website and they're doing some kind of change on their website, and then they want to study the effect of that change on some metric. You can define any kind of metric. One thing could be that firm basically, as the traffic is coming in, randomize. They use a random number generator and use that to decide what whether this new individual is going to see the site in the previous state or after the change, right? This randomization, what it does is basically is not allowing that individual to make the decision. The manager or the decision maker or the researcher is making the decision, is imposing a decision that was created through a randomization. In an observational study, the individual themselves make a decision whether they are going to get treated or not. Okay, and so in that particular case, there might be other sort of characteristics of that individual which may be different from the untreated individual. So to give you an example, right? So you did a PhD in machine learning, and hence you would have a particular salary level, right? So now the question is, that PhD in machine learning, is it the salary at the end of after your PhD that you received, was it really because of that getting your PhD, or was it because you were able enough to get into the PhD program? Like if you were to compare somebody like you against somebody who did not get the PhD in machine learning, and you were to compare their salaries, you have to take into account also people who go on to do a PhD in machine learning have a particular set of skills to begin with. They have the ability, number one, they have the ability to work hard. They have a particular sort of, endowment of intelligence and so on. So the comparison between a treated and untreated individual will only hold if you can find, individuals that are very much like you, but they did not do a PhD. So that would be the comparison. If, on the other hand, if you could go into a high school class and hypothetically sort of randomize that these 50 students from this 100 students, out of them 50, at random will do a PhD in machine learning and 50 will not. And then after 10 years, compare their salaries. That would be a fair comparison, but that would be a randomized control trial, which you cannot do in most cases. However, the second one is there is no explicit randomization. Hence, the treated and untreated individuals are not going to be similar in characteristic. I think that kind of is the crux of the problem. When you do not randomize, there is no basic guarantee that the individuals that are receiving a particular treatment versus the individuals that are not receiving a particular treatment, they are basically not going to be similar, except by chance. Does that answer your question?
Yeah, I think that answers the question. So basically, observational studies are randomized trials, not necessarily randomized controlled trials, right? So I think that's probably, if I summarize this. So it makes sense. Yeah. Thanks.
Yeah. So we would generally don't use the word randomized at all here. Even if you stand outside. So this, you may have heard about sampling, which is slightly different because right in this particular case, we're talking about randomization of a particular treatment. But in sampling, you may have heard the word convenience sample, right? Which is essentially that if you stand, let's say if I go and stand outside a mall and, as people come and, I ask their opinion about some social issue, and then say that this is what they're saying, that people who are coming may appear random, but they're not necessarily random. When we're talking about randomization, it has to have, like particular properties, which I'm not going to go into detail, but just for the sake of simplicity, you have to use like a mathematical random number generator, such as a hash function or something like that, which ensures that the where you assign an individual is actually random, which basically another way to say it is that the probability of each individual into landing in one bucket versus the other is exactly the same. So if you are doing a coin toss, right? If you're going to decide based on a coin toss whether a person would be treated or untreated, then every individual, like a priori, before we do the trial, the chance of you being treated versus untreated is 50-50. And the chance of me being untreated versus treated is 50-50. The chance of Nathan being untreated versus treated is 50-50. So it's completely driven by chance. And hence, for this example, we will use the term randomization. Haphazard things that are haphazard may not necessarily be randomized in essence.
That makes perfect sense. So thank you.
Sure. Okay. Other questions before I kind of move on? I think this is going to be, please go ahead.
Oh, sorry. Yeah, one question about second order effects. And it looks like you're looking at decision-making in complex systems like firms or governments. And it seems like trying to isolate one decision is going to run into the problem of all these unintended consequences and interlocking systems that would be affected by that one change. So I wonder how you account for that. Yeah.
I didn't get your name. So whoever asked the question, if you can just tell my name so I can also.
Oh, sorry. This is Sean.
Sean. Yeah, Sean, that's an extremely good question. It's a very, very good question. The finding of causal effects, or what is known as identifying them, is under very strong assumptions usually. And one of the assumptions is essentially these lack of spillover effects. If you have spillover effects, it's a much more complicated problem. This is a complicated problem in itself, but if you have spillover effects, then it becomes even more complicated. And there's basically a whole body of literature on how to deal with it and when you can deal with it and when there's situation is hopeless. One good example of what you're talking about, just to confirm, I'll give you an example and see if that's what you mean also, just to confirm. You may think about vaccination, right? So vaccination has an impact on like, say, for example, if in this house, in my household, if two people are vaccinated, that basically affects the possibility of disease for the others too, because now, so there is kind of a spillover effect, right? So if I get vaccinated, there's going to be a positive impact. If the vaccine is effective, there's going to be a positive impact on everybody else around me. That's kind of a spillover effect. And I think sometimes people who are opposed to vaccination are basically counting on that sort of effect, right? So if 99 people are vaccinated and one isn't, then that person also benefits from the vaccination of 99 others. And that's a spillover effect because that 100% was not vaccinated. Is that kind of the thing that you're referring to?
Yeah. I was just thinking that, if you change your backend for your business to a different software system, and then all your engineers struggle to figure it out, and maybe they were super competent the last one, it might look like that software is worse, but it actually might be better. It's just you didn't account for having to do the change management over to the new team.
Yeah, so basically we want to isolate. So usually these analyses are done under the assumption that is known as everything else being the same. And in some cases, that assumption can be met. In other cases, you may not be able to meet that assumption, and hence either the analytical problem is kind of hopeless, or there are more advanced techniques that you might be able to do. So the companies like although they're doing randomized control trial, but companies like LinkedIn, for example, does a lot of experiments, randomized control trial on their website, and they're worried about spillover effect of these various interventions that they're doing, and they have these firms have kind of developed these methods to deal with these issues, but it is a hard problem, and spillover effects make it even harder. But there are techniques that you can use in certain circumstances to sort of find the effect. But it was a great question. Thanks.
Yeah. So Zia, I don't want to keep you stuck on this slide, but I think a point that may be relevant. So when I was working at Microsoft and Bing Ads, we would first run randomized control trials, but after a while, we will actually go back and do counterfactual analysis just to understand what actually happened, right? So because randomized control trials, they may have their limitation. And what we used to do was we would go back and do counterfactual on after to understand what basically more causal inference. But just to mention that both can be done at different times on the population, right? So that's also possible.
Yeah, absolutely. Thanks so much. And your point is absolutely correct that a lot of firms are now the top firms, Microsoft, Google, Lyft, Airbnb, Uber, LinkedIn, people who have large data science teams, they have basically developed sophisticated groups around causal inference too. But I think this is going to percolate as machine learning is percolating down, or predictive analytics is percolating down into other firms which are non-tech. I think causal inference is also becoming used more broader and broader. And I think this is, in a way, for managers, very important. So, one example that I can give you is a retail chain was trying to figure out whether what would be the impact on their business if they change their hours of operation by 1 hour. So if they reduce their hour of operations by 1 hour, what would be the effect? So you can think of short-term effects. Maybe if you reduce the hour, the drop in revenue may be larger than the savings you get, right? Or it could be, some kind of long-term effect that in the short term nothing happens, but in long term you lose customers, and so on. These things people used to sort of argue and decide, but now firms, even retailers are running randomized controlled trials to figure that out. So in addition to firms like Raja mentioned, Microsoft, were very sophisticated, there are even firms that are not traditionally thought of as very somewhat less sophisticated than Microsoft in data analytics, but they're using these techniques. Okay, so let me get to sort of the study itself. Here's the preview of results. And I'm just giving you a preview, and then I'll go a little bit more detail if everything isn't clear. Hopefully it will by the time we get through the slides. So leaderboards, on health wearable devices result in about 3.5% increase in daily steps, which is about 84,000 steps in aggregate for the average adopter. This effect is highly heterogeneous by prior activity level, whether the individual was sedentary or highly active, the size of the leaderboard and past week's rank. And what we found is that the previously sedentary users, who were not very active, see sort of a 15% relative increase, but previously highly active users see a 5% decline. So why is this important? So this is really important because, in the medical community, the literature has been, physicians and others in the health community have been concerned that whatever interventions they come up with, they generally tend to benefit people who don't really need it much. So people who are very fit and highly active to begin with, they are the ones who will get motivated with things like leaderboards, and it will not sort of encourage people who really need it more. So the sedentary users, you need the intervention more, but the medical community was concerned that it really doesn't help. And this kind of evidence shows that that it is helpful. So number one, this finding is helpful to sort of policymakers or the healthcare community or to individuals like us. On the other hand, this kind of information is also useful to a manager within Fitbit, for example, the health wearable device that we studied, because if their users are benefiting more, they're more likely to use Fitbit and keep coming back to Fitbit to buy more devices over time. And hence, they want to, if they want to, increase engagement with the user, this kind of information that a particular feature of the platform is beneficial is useful information. Okay. Another is the number of active users on leaderboards increase benefit initially, but when leaderboards become too large, it starts to hurt. Okay. So that's kind of the preview of results. You can keep it at the back of your mind. And I'm going to try and convince you and show you how we kind of make these claims. Okay. So I'm going to now go back and try to fill in some things just to make sure everybody comes along. So the question is, what is a health wearable device? A wearable device or a computer app, it's a health wearable device. It's a computer application that records a person's daily physical activity together with other data related to their fitness or health. So, Fitbit or Apple Watch, which I don't really use, so I don't know all the features it has. But generally speaking, they measure step count, and they're fairly accurate for step count. They also measure your heart rate. That's slightly less accurate. And of course, things like number of calories burned and so on, which have a lot more measurement error. So these are the things that these devices measure. For our case, the outcome that we're looking at is step count, for which they're generally quite accurate. And people have compared them to gold standard measurements, and they're fairly accurate with that. Okay. So the general motivation of the study is that there's a broad adoption of, and this is one of the fastest growth area in any wearable technology, health wearables. And the other thing was that if you just look at health wearables themselves, like a Fitbit device or an activity tracker, there are studies that people did, and they did not find benefit for these health wearable devices in itself. So just wearing a device may not be helpful, but if you combine it with other kind of interventions, right, things like leaderboards, maybe they will be helpful. And for a Fitbit manager, I mean, this is very useful because people might buy a wearable device, and if they don't see any benefit, they'll basically go back to regular watches or not wearing a watch because they really don't see any benefit from it. Okay, so the gamification of Fitbit is done using leaderboards, which rank individuals by step counts. The leaderboard here, you may have a lot of times when I give a talk, or one of my co-authors give a talk, individuals, people in the audience have used leaderboards, or they may be familiar with leaderboards. So I'm going to basically explain Fitbit has a particular kind of leaderboard, and so it is slightly different. So because this is the main thing that we're studying, it's really important for us to explain what this leaderboard is. Okay, so there's a chat, something in the chat. Okay, so it's basically, I don't think it's a question. So here, essentially, the leaderboards rank individuals by step count, and through the ranking against other participants, the leaderboards, influence a participant's activity. And in the case of Fitbit, it's basically the 7-day rolling step total. Okay, so let me show you what the leaderboard looked like. So here I have pictures of four users, and this is the Fitbit leaderboard for these users. So Ash, Dave, Mary, and Todd. Let's start from the left side. So Ash has basically 3 individuals on her leaderboard. So Mary and Todd. And if you look at the leaderboard, Ash is actually second, and these numbers here are basically the number of steps done in the 7-day period. Okay. The second person, Dave, has a different leaderboard than Ash. Dave is only connected to Mary, and Dave is basically number 1 on his leaderboard. Mary, the third person, there are 4 people on the leaderboard. So you have Dave, Ash, and Todd on her leaderboard, and Mary is sort of number 2 on her own leaderboard. Dave is number 1, and then Todd, likewise. So essentially, what you would notice here is, compared to some of the other leaderboards, where you may have, like on a platform, there may be one leaderboard. I think this is quite common in gaming and stuff, video gaming, where there's a leaderboard and there are thousands of people. Instead, over here, these are leaderboards where you only have people that you kind of allow them to join your leaderboard. You only compete with people, a group of people that you have really agreed to connect to. Is that clear? Is that distinction clear? Any questions on the leaderboard? Okay, so Sean says this is all good. So let's go on to, so I'll show you, just very quickly. I basically made the mistake of, I was doing the study, so I said maybe I should also learn about eat my own dog food kind of thing, wear a Fitbit device and have a leaderboard and compete. And my mistake was that I kind of invited my son who was a teenager, to compete with me, and it was kind of brutal. So if you go, the way to read this is go from bottom to up. So this is a little bit old, but so he starts a little bit nicely. Then I get egg on my face, and then it starts to get quite aggressive. I think you might be losing right now. I don't know for sure. You're 2x here. So he was doing twice in a day what I did in a week, and so on. And so he was, by the end, he was doing 100,000 in a week. And I don't know, maybe I was a few thousands a day. So the moral of the story here is choose people wisely who you let in your leaderboards. Let's see, somebody else has a question. Okay, I think it's just a comment. So I'm going to just, if there is a question, maybe I'll just request Nathan to prompt me, so I keep going. Okay, so so the study setup is following. So we gave this Fitbit charge HR devices to about 500 undergraduates at University of Notre Dame. Students were compensated for providing physical activity data, but they were not. So they were only compensated for physical activity data. They were not compensated in any shape or form for being more active. Otherwise, the effect would be because of the payment, not because of the device. And then we also collected detailed survey data on these participants, and about half of these students adopt leaderboards, and around 2 years of physical activity and leaderboard data was there. So if you think about this is an observational study because these students themselves decide that they want to adopt leaderboards. It's not, we cannot randomize without making these leaderboards unnatural. We want them to be very natural leaderboards, and we want people to connect to whoever they want to, rather than forcing them to connect to particular individuals, which randomization would entail. Okay, so the treatment here is leaderboard adoption, people who have leaderboard, and the outcome is the number of steps. So you have to really remember the leaderboard is a treatment, not the Fitbit device. Every individual in the study has a Fitbit device and they use it. Okay, so in terms of model, this is basically a regression model that we are going to do, and as I mentioned earlier, both machine learning or predictive analytics as well as causal inference use similar statistical techniques. However, the goals are different, and the assumptions that are necessary to achieve the goal are also different, right? So here, if I may just expand, I'm going to be, so individuals are basically indexed by the I, and time period are indexed by T. So we observe these individuals over a two-year time period, but our unit of analysis is an individual in a particular week. So we are going to be measuring their number of steps every week, right? So let's say, Raja is individual number 1, and he's also observed over 2 weeks. So, S1 1 could be his number of steps, Raja's number of steps in this particular week, and so on. And then we also observe whether this particular individual had sort of leaderboard adopted in that particular week or not. And leaderboard adoption is kind of what is known as sticky. So once individuals adopted, they kind of stay with it. Okay. So people who have studied causal inference, or especially econometrics, if they're on this call, this is essentially a staggered difference in difference design for observational study. And I'm happy to talk more if people are interested in how the identification works. But essentially, this is we're going to regress the number of steps that an individual has in a particular week on their adoption status, which is the leaderboard adoption status here. And we also will have a number of controls, which control for the individual's characteristics. And this regression would basically help us identify, under the assumption that individuals that did not adopt a leaderboard are very similar to the individuals that did. That is kind of the identifying assumption. Okay, so here's kind of the result in summary. So the first 2 columns basically are different in terms of the individuals, the number of controls we use. But what we find is, in our most complete model, which is column number 2, what we find is, individuals that adopted leaderboard had around they basically do 370 more steps per week. So that's kind of the 370 more steps daily on a daily basis. That's kind of the effect that we find of leaderboard. Okay. So you might wonder whether these individuals that are using leaderboard and those who are not, whether they're similar or not. And there are various techniques in the literature. One of the techniques is what is known as inverse probability of treatment weighting, where you can what you could do is you can use this technique to actually, if the individuals that are treated and untreated, if they're not very similar, you can statistically make them similar. So here sort of these is a chart. On the right hand side is a absolute standard difference or standardized mean difference, which is basically the difference in mean on the number of steps between the individuals that were using the leaderboard versus that were not, divided by the standard deviation. And here, the first sort of on the horizontal axis, you have the unweighted and weighted individuals. And in the beginning, what it's showing here is these basic circles are various observed covariates. So it could be covariates like the gender of the individual, or their, the year that they are in, the family income, and so on and so forth. What the left side of this chart shows that there's a lot of difference in when you without this adjustment, but after you kind of adjust, the difference drops to less than 0.2, which is kind of the sort of rule of thumb used in ensuring that the two groups are kind of similar in their characteristics. Okay, so after you balance, what you get is results which are consistent that we got in the first model. And because these quantities are never observed, this is like a very big distinction between machine learning and causal inference. In causal inference, the quantity that you are trying to predict is at least observed for your training data set, and so on. So, however, in causal inference, you're basically what you're trying to estimate, if I go back to the slide, is this beta, which is kind of the effect size. This beta, only God knows. Nobody knows for sure what this data is. It's never observed. You can only sort of estimate this beta using some very strong assumptions, in generally speaking, and less strong assumptions if you are able to have a randomized control trial with no spillover effects, as as Sean basically asked also. Okay, so so basically, I'm going to skip a few things just to get into some more details about our findings. So one of the things that we looked at was what could be the effect. We were thinking of what could be the effect of the size of leaderboard. So you can have leaderboard size may have diminishing returns. So if the leaderboard is too small, you may gain more from the feedback, right? So if you're too small, it may be like a smaller and more intimate group of your friends, and you may get more feedback, and you also avoid being stuck at the bottom. If it's too large, you may have anonymity in the crowd, and you may have weaker ties with some participants. So what we're trying to see is whether the effect size kind of varies based on some observed characteristic, and one observed characteristic is the size of the leaderboard. So the way you kind of estimate that is again by using regression models, and what you will do is throw in some interaction terms, which I can talk more if there's interest, but essentially you interact the treatment with these various interaction terms. So let me just explain what we mean by it. So let's look at column number 3. So here, basically, what we're doing is we're trying to find the effect of leaderboard, by the size of the leaderboard. So if you look at the main effect, it's basically a null effect. It's a small negative number, which is statistically not significant. However, if as the number of users increase, the number of steps that you're going to take is also increases. So if you have basically 10 active users other than you're basically gaining about 334 times 10 steps per week. But this is also moderated kind of, or there's kind of a diminishing effect because of this square term, which is minus 21. So if you have 100, so if you have 10 users here, so 10 squared is 100, and if you multiply this, that would be minus 21 times 100, minus 2100, and then you add them together, so you get about 1,000 steps as an effect. So here, kind of this figure actually shows you how the effect kind of varies. So here, if the leaderboard is very, very small, or there's no other active users, you basically have no effect. As kind of the size of your leaderboard increases, you start to gain more benefit out of the leaderboard. But if it becomes too large, if you have too many people, you kind of this effect tapers, and then you start to sort of lose any benefit from this leaderboard, and very, very large leaderboard are not going to be very useful. So this is useful for an individual that's participating, but it's also useful for firms. So Fitbit manager may look at this and think, do we need to somehow think of how to design our leaderboards so the leaderboards don't become too large. Okay, so in that particular way, it might be useful. So I have some more results and also a full paper, but because we're getting close to the hour, let me just open it up for any questions or comments, and also mention that I know all of you who are attending are really interested in data science and using data for decision making. If you have a problem that may be of a causal bent, please feel free to reach out to us. And if there is a possibility of academic collaboration, I'm not talking about any kind of monetary consulting. It's basically just academic collaboration. We can have a conversation, and if it's useful, we might be able to work together. So let me just open to question or comments, and then we can close.
So Zia, I have a question, but I will let others go first because I've already asked a question. But I do have a
absolutely, yeah.
Call it comment. But I would let others go first if there's anyone who has a question. Okay, so in that case, I think I will go and present my question, or maybe my comment first. So I don't know how many of you are familiar with this anecdotal Facebook 7 friends in 10 days. Anecdotally, in early days of Facebook, someone did some sort of analysis on Facebook user and who the users who are sticky, who stay. Someone actually came up with this idea, just like, number of active users is 10 and you get the maximum number of steps, the most effectiveness. So someone came up with this, that if you can get 7 friends in 10 days for a new user, they are going to stay with the platform, right? So such is the power of causality, right? So, and then you can see if this kind of insight you can get, you put all of your resources into getting 7 users in 10 days. And in this case, if Fitbit were a manager at Fitbit is looking, let's try to incentivize or optimize the leaderboard sizes around 10, and then, just come up with ways where you keep these sizes around 10. So that's the comment. My question was, I see there was a segment of people who were already somewhat active. They saw lower gains or lower ROI, or just whatever we want to call it. And people, I think the number was 5 and 15 for somewhat active users on average, had a, there was, I saw some comparison, right? Did you do any other segmentation by gender or maybe, their income status or anything that you may have known?
Yeah, this is a great question. So here is that sort of slide that I kind of skipped, and just to quickly give you tell you the legend. So S is for sedentary, mid is for mid 50 percentile, and H is highly active. So we broke them down by 25 percentile, 50, 75, and the top. So highly active is the top 25 percentile. So if you look at the column first and second, basically 1365 steps for the sedentary users, which is positive, and then negative 630 for the highly active user, and then we further break it down. For these other characteristics like gender and income, household income, we did have data, but we actually did not sort of find any meaningful differences in these effects. So the effect sizes, at least in our sample, did not vary by those observe characteristics of individuals. The things that we found was whether, their prior activity level, that was one source where there was some heterogeneity or differential effects. The second one was size of the leaderboard. So first is a characteristic of that individual, what state they were in the past. The second one is a characteristic of the leaderboard that they formed or they joined. And then also, there was an effect of whether you got a rank of first in a prior period. So it goes to this thinking that if you, which as a professor, I'm kind of aware of, is if a student gets an encouragement that basically sort of excites them and to excel in the future, essentially. So if even a sedentary user was first, that basically leads them to even a higher effect. So if you look at column number 4, the effect, this particular sedentary the sedentary users in column number 4, the effect if they were first on LB is actually 1262 plus 745, which is about 1900 steps, which is a decent amount, like almost 2000 steps a day that they're gaining in their performance. So these were kind of the things that we found effect heterogeneity around, not in some of the other characteristics that you were asking.
Yeah, thank you. Yeah, that makes sense.
Sure. Other questions or comments?
Sure. I was wondering about if you did any follow-up on actual health outcomes, because you could have a situation where someone on a leaderboard would just wear the Fitbit more to try to stay up on the rank, but the other person might be doing just as much physical activity, but just not be as competitive. So did you do any outside validation on outcomes?
Yeah, so this is a great question, but we could not. The most we did outside of actual this automatically collected data was the surveys. Given the size of the study, there were 500 students and giving out these devices and so on, then getting them in and doing their the health study while it would be extremely useful, I think operationally it was very hard for us.
I get that. Did you were you able to investigate any outliers? Like it's someone that you would have predicted to do really well. Maybe they broke their foot, or someone you wouldn't have predicted to do well joined a sports team. Were you able to, through the surveys, see any explanation for some of the outliers?
So the way, if I understood your question correctly, I can give you a two-part answer to this question. So the first thing is, I think you're concerned whether somebody who's an outlier in their behavior is actually moving the effect size to be too large. Is that kind of the concern?
Right. Someone that, by all the survey data and their leaderboard participation, would have been predicted to be a high stepper, then they have a foot injury and they don't step for a few weeks or something.
Okay. So they had something that changed for that particular individual, which was kind of a shock. So the short answer is we did not collect that information separately from the actual data that was collected. The thing though is the one way to think of this whole design is the following, right? That let's say, Sean, you're working out and I have data on you, and you basically adopt leaderboard, and I have data on you before and after adoption. And I have, a large number of observations in the pre-period and a large number of observations in the post-period. If this particular shock, let's say, for example, the shock that their foot was broken, if that's transitory, it's very short period, the average in your post period is not going to vary very much because we're dealing with averages over a long time period, right? So let's say, for example, over a 2-year period, and I have daily data on you, you did not exercise for a day or you forgot to wear your Fitbit watch. Your average over the 2-year period, daily average, is not going to vary very much. However, if I have data on you for only 2 days and you only exercise for 1 day, the average would vary a lot, right?
Right.
So I think the way we kind of deal with this issue is through that that we have data for a long time period before and after. That's one thing. The other thing I can kind of mention is I think I may have the paper. Let me see the paper. So that's basically the same. I want to just show you quickly. We also do some, what is known as outlier analysis, where one of the things that you can do is essentially drop people from the sample and re-estimate. Okay. So here's kind of the chart to do that. Here, the kind of the thing that we're trying to guard against is whether a particular individual is kind of driving the result, right? So an outlier may be driving the result, and let's just look at the top, which is the top chart here in figure F3, which is basically the effect size. Okay. What we do is we kind of estimate the effect by leaving one individual out. So I'm looking at the top left chart from these 6 ones, and the thing we're trying to guard is whether this particular individual is so influential that it basically increasing the effect size too much. But so we systematically leave out one from the sample of about 500 individuals, out of which 250 were adopted, and then try to estimate with this new sample each time. And then this is kind of the distribution of the effect size. This is a box plot. And you see that the effect size kind of ranges between 331 and 404. So, no outlier on either side is kind of driving this result. Or at least we don't find evidence for it in the data.
Yeah, that's really, really useful. Thanks.
Sure. Other questions or comments?
All right, it looks like there aren't any more questions. Thank you, Zia, for presenting this, even though we didn't have time to quite get through it all. I think everybody found it interesting and incredibly useful. We did record this webinar, so we will have this up on our YouTube channel and on our website here pretty soon. If anybody has any questions for Zia, I'm sure he'd be happy to connect with you on LinkedIn. And thank you for joining.
Thank you.